everybody? Okay. So we, towards the end of Thursday's lecture, we started discussing about the third assumption of the particulate model of matter, which is, okay, particles interact with each other. Okay, the three assumptions are now matter is made of particles. These particles move all the time. And the third one is particles interact with each other. And that assumption, the third assumption, was crucial for us to model dense phases like liquid and solids. Without that, without the third assumption, we cannot do that. Okay, and then we talked about like where we have strong interactions and stuff like that. This is just to remind us about what we have done so far. Here we go. 1 minute in your groups. We answered the same question on Thursday as well. Okay. And here are our responses. Look at that. It's beautiful. Okay. Most of us know that if we want to have stronger interactions, okay, you need to be closer to each other. That's the idea there. Okay. In solids, we have the particles closest to each other. As a result of that, the solid's going to have the strongest attractive interactions between the particles. Okay. On the other hand, in the gases, we have particles furthest apart from each other. As a result of that, you're going to expect the weakest attractive interactions between the particles. The mantra goes like this. The stronger the attractive interactions, okay, interactions, the lower the potential energy. Anybody who can remember that? Yes, sir. Thank you. When the particles are furthest apart from each other, meaning that when there are no interactions between the particles, the potential energy was set to 0. That's our reference point, because we need to start somewhere, and then we need to start from where, things are not likely to change. When you have particles infinitely far apart from each other, okay, that seems like a good reference point, and that value was set to 0. And then when we move the particles closer to each other from that point, okay, we decided by convention that the potential energy goes down. That means potential energy is going to become negative. And then when we have the particles closest to each other with the strongest attractive interactions, we have the lowest potential energy possible. Okay. And that's like a solid. Okay. That's the lowest potential energy possible. And if you try to push the particles even more closer to each other beyond that point, the potential energy is going to be highly unnatural, and it's going to shoot up in the positive direction. Okay. So anyway, so that's the idea of that. It is stemming from this mantra is stemming from that. The stronger the attractive interactions, the lower the potential energy. Okay. Do we have any questions, concerns, comments so far? Okay. So let's do one thing. We'll combine this mantra with what we just decided in the previous question and see if we can do something like this question. Here we go. For the 3 phases now, again. Most popular answer, okay? And that's the correct answer as well. 85% of us, have this answer, okay? And I have a feeling that some of us flipped it, okay? Accidentally. That happens too. But apart from that, hi, Hannah, do we have any questions, concerns, comments? If you just flipped it, I reopened the question, you can fix it. That's not a problem. But do we understand each other? Do we have any questions, concerns, comments at the moment about this?
Okay. When we order them, like when asked to order the increasing potential energy, do we do from lowest potential energy to highest, or highest?
If it's an increasing order, so you start with the lowest, and then you're gonna go with the highest at the bottom.
Okay. Thank you.
Yeah. Let's do this. Okay. Now, we have an idea about the potential energy. The stronger the attractive interactions, lower the potential energy. The solids will have the lowest potential energy because it has the strongest attractive interactions between the particles. That's the idea. And the gases will have the highest potential energy because gases gas particles are farther apart from each other, meaning you have the weakest attractive interactions. Weakest attractive interactions, high the potential energy. Right? So that's the idea behind this order we have decided on. All right. So for this problem, we did temperature versus time. Okay. And then we noticed how the temperature was constant during phase changes. And we also did, let's see, also did put the total energy versus temperature. Okay. We discovered vertical regions in potential in total energy versus temperature diagrams, okay, or graphs. And then today we're going to do the potential energy versus temperature, and then maybe kinetic energy versus temperature, which is pretty straightforward. So I'm going to do a few things here. Okay. So I'm going to do first, just to remind us about what we have done so far. Okay. I'm going to do total energy, change in total energy as a function of temperature. Okay. So let me say delta E total, the first one. Okay. And let me zoom in a little bit so that you can see what I did. I just wrote total here, E delta E total, meaning potential energy plus kinetic energy. All right. So we know when we start heating the sample from -5 to 0 degrees Celsius with temperature, the energy increases. At 0 degrees Celsius, the temperature remains constant, but system keeps absorbing energy to convert solid to a liquid. Okay. Once everything is converted to a liquid, then again, with temperature, the energy increases up to 100 degrees Celsius. And at 100 degrees Celsius, again, the temperature remains constant, but system will keep absorbing energy to convert liquid to a gas. Okay. And once everything is converted to a gas, then again, the total energy increases with temperature until our endpoint of the experiment, which is 105 according to top hat. Okay. So we have liquid here and the gas here. Okay. That much we know. And then what we also do today was, to think about how the potential energy changes with temperature. Okay. And this is how it goes. So with temperature, the potential energy changes very slightly. Okay. So from -5 to 0 degrees Celsius, there's a slight increase in potential energy. Okay. But at 0 degrees Celsius, when the solid becomes a liquid, okay, there's a huge jump in the potential energy. Why? The strong interactions in the solids are weakened so that it becomes a liquid where we have weak attractive interactions. Weak attractive interactions means higher potential energy. So at 0 degrees Celsius, temperature remains constant, but the potential energy increases a lot. Okay, remember this, we're doing the potential energy here. So let's call it E sub delta E sub P. Okay, so again, at 0 degrees, the solid is becoming a liquid and the potential energy increases a lot. Okay. Then again, once everything is converted to a liquid, okay, the increase of the potential energy with temperature is slight, okay, is minimal until the 100 degrees Celsius, where you have another phase change. Again, at 100 degrees Celsius, the temperature remains constant, but there's a huge increase in the potential energy to convert liquid to a gas, because we have the weakest attractive interactions in the gas phase, meaning very high potential energy compared to a liquid. And that's why this vertical line is actually longer than solid to liquid one, because we have to change the potential energy a lot. And once everything is converted to into a gas, again, there's a slight increase of the potential energy with temperature like that. Okay, that's potential energy versus temperature. Lastly, okay, the kinetic energy, that's the last thing I asked you to do. Let me call it delta E sub K for kinetic energy. Okay, so this one is straightforward. If you increase the temperature, so we know temperature is a measure of the average kinetic energy. If temperature increases, the kinetic energy must increase, meaning between temperature and the kinetic energy, you have a linear relationship like that. Okay. Okay. Now, one question I got was about the kinetic energy versus temperature. So what's happening during phase transitions? Okay. you cannot indicate a phase transition in a kinetic energy versus temperature graph. Okay, imagine, all right, imagine that we had, can I borrow a pencil from somebody? I only have blue, black, and red pen. Okay, maybe I can steal one. Give me a second. All right, imagine that somebody drew a step here like this. Okay, and it goes like, I don't know, something like that. Okay, what does it mean? This shows that temperature remains constant at 0 degrees Celsius, but the kinetic energy increases. Can this happen? No, this can never happen, because temperature is a measure of the kinetic energy. If one increases, the other must increase. Okay, if kinetic energy increases like this, the temperature must increase. Therefore, you do not have steps in kinetic energy versus temperature graphs like that. They are linear. They are directly proportional to each other. Right? That's one of the questions I got. Do we have any other questions, concerns, comments at the moment? Anything? Okay, let's do one other thing. Okay, this is a bonus one. So just to remind us about temperature versus time graph, okay, for the same process, all right? So we are starting at -5, and then we have the 0, then we have the 100, and then we have the 105, and so forth, right? So with time, temperature versus time, okay, if you're heating at a constant rate, the temperature increases with time, okay, until 0 degrees Celsius. At 0 degrees Celsius, okay, time goes on, but the temperature remains constant. Okay, why? Solid is becoming a liquid. During phase changes, temperature does not change. Okay, and once everything is converted to a liquid, again, the temperature increases with time until 100 degrees Celsius, and at 100, again, the time goes on, but the temperature remains constant. Why? Liquid is becoming a gas here. During phase transitions, temperature does not change. Okay, and once everything is converted to a gas, again, temperature increases with time, like that. Okay, so we have solid, liquid, and gas phases in these ramps. Okay, now my question is this. Okay, on your whiteboards, I want you to draw how the kinetic energy changes with time for the same process. Go ahead. Same as temperature versus time, right? We know, okay, temperature is a measure of the average kinetic energy. Okay, in other words, temperature and kinetic energy are directly proportional to each other. Okay, meaning if you draw the kinetic energy versus time, it should look the same as temperature versus time, right? So it should look same thing like that. So increases, stays the same, and then increases, stays the same, and increases. What these values are for the kinetic energy, I have no idea. Okay, but I know that they need to be above 0, because kinetic energy must be greater than 0. Okay, and if you have delta kinetic energy, that means you can start at 0 at the starting point. That's the only difference between delta kinetic energy versus kinetic energy. All right, back to the triple point of water again. So, okay, let's start with the third one. This is the most recent concept we learned, right? In which phase do you expect to have the particles with the strongest attractive interactions? Okay, almost like more than 90% of us say that it's going to be the solid phase. Okay, the others, I believe, is closer to, I don't know, 80%. Okay, so in which phase do you expect to have the highest average potential energy per particle? Gas. Okay, why? In gases, we have the particles furthest apart from each other, meaning weakest attractive interactions. Okay, the weaker the attractive interactions, the higher the potential energy. Okay, that's the, so again, this is going back to the mantra we drew. I mean, we wrote in our notes. Okay, the stronger the attractive interactions, the lower the potential energy. And the other way around is the weaker the attractive interactions, the higher the potential energy. Right? So in gases, we have the weakest attractive interactions, meaning we have the highest potential energy. Okay, so that is that. And then the first one is about, reminding us about temperature, relationship between temperature and the average kinetic energy. We know at the triple point, all three phases occur at the same temperature. That's just one point, triple point. Okay. Meaning they should all have the same average kinetic energy. And not only that, they all have the same mass as well, because we're talking about the same water particles. And as a result of that, we have proved to ourselves, then they should have the same average speed as well. If the mass doesn't change, then the speed must be the same as well. Average speed must be the same as well. Okay. That's why what you're looking at is the correct answer, are the correct answers for those questions. All right, I'll get us some data about the boiling points of these substances, normal boiling points. Okay, what I want you to do is I want you to arrange them in the order of increasing attractive interactions between the particles. Intermolecular forces, so IMFs, means attractive interactions between the particles. Okay. The most popular order, okay, acetone has the weakest attractive interactions. Then octane, on the other hand, at the other extreme, has the strongest attractive interactions. And this is the correct answer as well. 71% of us got that. And some of us flipped this. I know that. I know that for a fact. All right. Do we have any questions about this?
Attractive forces between the particles is lower, which is why it goes from acetone being the lowest and octane being the highest.
Okay. Okay. Thank you so much, Zia. Okay. Yeah. So what she just said was this, right? So boiling means we are going from liquid to gas. In the liquid, we have strong attractive interactions than in the gas. That means when you go from liquid to gas, we need to weaken the attractive interactions between the particles. In acetone, we need to provide lesser energy to do that. That means it boils at a lower temperature, meaning we have to provide lesser energy to weaken the attractive interactions between the acetone particles because they have already weaker attractive interactions. On the other hand, octane has the highest boiling temperature, meaning you need to provide more energy to weaken the attractive interactions between the particles in octane so that it can go from the liquid phase to the gas phase. Yeah? All right. Now, the thing here is the stronger the IMF, meaning attractive interactions between the particles. IMF stands for intermolecular forces. This is synonymous with attractive interactions between the particles because we haven't talked about molecules yet. We mean the same thing. Okay. And the idea is the stronger the attractive interactions between the particles, okay, higher the boiling point. Okay, we just discovered that. Not only that, higher the melting point. Okay. Higher the density. Okay. Higher the viscosity. Okay. What else? Anything else you can think of? Higher the condensation point, higher the freezing point. All those points are higher if you have stronger attractive interactions between the particles. There are some other things which are lower with strong attractive interactions. Those are like, if you have strong attractive interactions, we have lower vapor pressure. Why? If you have strong attractive interactions between the particles, okay, they are less likely to come out from the liquid phase to the gas phase because they are held strongly together in the liquid phase. Therefore, the vapor pressure decreases. Okay. And then the next one is, okay. Here's another question for you. This time I'm going to give you some, yeah, the same thing. I think, this is the first question I gave in the beginning of the class, right? Okay. I want you to, again, try the same problem. This time I want you to arrange them in the order of increasing potential energy, meaning lowest potential energy at the top and highest potential energy at the bottom. Go ahead. Here we go. And here are our responses. The most popular response is this, and that's the correct answer as well. 61%. All right. I know that some of us still flipped it. No matter what I do, We tend to flip it sometimes. Okay. Anyway, what questions, concerns, comments do we have at the moment? Okay. So we put octane at the top because we have strongest attractive interactions between the particles in octane. How do we know that? It has the highest boiling point of all the substances. On the other hand, acetone has the highest potential energy. Okay. And how do we know that? Because it has the weakest attractive interactions between the particles, because it has the lowest boiling point. All right. Okay. Here's another one for you. Look at that. It's beautiful. Okay. So close to 90% of us, more than 90% of us said that is sevoflurane. Okay. Sevoflurane has the strongest attractive interactions between the particles, and that's the correct answer as well. All right. So again, just to make sure that we have our thinking straight here. Okay. Sevoflurane has the lowest vapor pressure. This is this curve over here, right? Has the lowest vapor pressure at any given temperature. Okay. Meaning it has the hardest time to go from liquid to the gas phase. Why that is the case? Because you have the strongest attractive interactions between the particles, between the sevoflurane particles. That's why it is harder for it to go from the liquid to the gas phase, and that's why its vapor pressure is lowest. Okay. And on the other hand, some of us picked desflurane, but anyway, desflurane on the other hand has the highest vapor pressure of all, meaning it has the weakest attractive interactions between the particles, and that's why those particles go from the liquid to the gas phase most easily than the other ones. So, well, we should be very clear in our notes. The stronger the intermolecular forces, lower the vapor pressure, lower the volatility. Yeah? Yes. And we can explain that as well, why that's the case, using the particulate model of matter. All right. Now, do we have any questions, any other questions, concerns, comments before we switch gears a little bit? Anything, any questions, concerns, comments? All right. Now, we're going to have a preview of coming attractions now, okay? Now, the rest of the class time, we're going to think about, why things change, okay? Like we think about the processes, all right? So, now we're going to try to explain why would anything happen in this world using only two factors, okay? And those two factors are only two things, okay? Number one, the potential energy. We already know what potential energy is. It's about the strength of interactions between the particles, okay? And then the other thing is the number of configurations, okay? With using just those two factors, we can determine whether something should occur or not. Okay, that's it. Those are the only two factors we're going to consider. All right. Right now, we know that we understand potential energy. Okay, we talked about them, and then it's about the strength of interactions between the particles. Okay, stronger the attractive interactions between the particles, the lower the potential energy. That's the mantra we wrote in red in our notes. Okay, it should be written clearly in your notes. Okay, and now the number of configurations. How many of you do not understand what number of configurations mean? Can you see the hands? Configurations. Go ahead. I'm going to close this question in 5, 4, 3, 2, and 1. Okay. And most of us said that you do not know what is meant by number of configurations, but most of you picked dome room B, being the dome room with the higher number of configurations. So you know something. Yeah, and that's the correct answer as well, by the way. Right? Why? Anybody who picked dome room B, why did you pick it? How do we know that we have a higher number of configurations there? Anthony, Hannah, do you still have the microphone? Oh, there you go. All right. That's okay. What's your name, sir? Thank you, Anthony.
My name is Jack.
Go ahead.
There are more configurations in room B because there are more things to put in different positions.
More things to play. Okay. So what is number of configurations then, Jack?
It's the number of ways that the room can be arranged.
Thank you. It's number of ways or number of, that's what number of configurations means. Number of ways things can be arranged. Okay. When it comes to a dorm room like A, which is a clean, organized dorm room, there are only a limited number of ways you can arrange. Okay. Your clothes must be in your closet, and then your toothbrush must be in the bathroom somewhere, probably. And then your hat must be in the hat hanger. And then your TV must be there, without anything else. There are only certain ways you can have a clean dorm room, organized dorm room. But when it comes to, a messy dorm room like dorm room B, you can have many more different arrangements or configurations. You can have your clothes on the floor, on the TV, on the bed, in the bathroom, on a door, on a lampshade. Okay, you can have many ways of arrangements. Right? Toothbrush can be on the TV or on the floor, under the table, under the bed. Okay. So you can see that you have many more ways of arrangements or configurations for a messy dorm room compared to organized dorm room. Yeah. Now, here's the thing. Okay. Here's the question for you. Okay. What is more likely with time to have a dorm room like A or B? Everybody.
What it's leading to?
Yeah, the nature favors B. Okay, the nature favors higher number of configurations. That's why it is more likely if I walk to your dorm room in about 3 weeks from now, okay, I'm more likely to find a dorm room like B rather than an A. Okay, this is not you, this is nature. This is totally nature. Blame the nature, okay? Because now, everything happens to maximize the number of configurations, and that's why the messy dorm room at the top, highest at the bottom. Go ahead. And then gases have the highest number of configurations, and liquids are in the middle. And that's the correct answer as well. 90% of us agree with that. All right. Any questions, concerns, comments about this? All right, quickly. Can somebody explain why we have the highest number of configurations in the gas phase? Anybody? Anthony, you want to have a stab at this? Yeah, thank you so much, Anthony. All right, let's listen now, okay? Anthony, go ahead.
Okay, so solids are kept in a rigid structure, so there are less ways to arrange the particles, whereas gases are just floating freely in air.
Right, thank you. Yeah, so gases are like singles, right? Okay, they are not tied to someone or something or anything, all right? They have more freedom. They can be anywhere they want, just like gas, okay? But on the other hand, if you have a liquid or a solid, all right, you need to be, interacting with somebody else. Okay, when you are a couple, you have less ways, less freedom, or less ways of arrangement than when you're single, because you have to be closer to that person. Okay, that limits your number of configurations. Okay, now again, remember, the nature favors the higher number of configurations. Okay, and that's why sometimes in relationship things go south. Okay, because blame the nature. All right, I want to be with you, but I want my freedom as well. Okay, anyway, that's competition. Okay, anyway, do you have any questions, concerns, comments? All right, let's do maybe one last thing. Now, what we're trying to do here is to explain processes, okay? To explain why things happen, okay? Now, for an example, let's think about a process like boiling a liquid, okay? When it comes to any process, okay, there are two states, the initial state and the final state, okay? If you think about the process of boiling, What's the initial state? What do we have in the initial state? Everybody. Thank you. It's the liquid. Okay. Before boiling, you have the liquid. And after the process, in the final state, what do we have? Yeah, the gas. Okay. So that's the final state. The final state is consists of gas. Now, what I want you to do is, I want you to put these two states, the initial state and the final state, in a diagram. Okay. In that diagram, I have potential energy on the y-axis. Let me write that. You have potential energy on the y-axis. And then, what do you call this sign again? Don't call me hashtag. Hashtag is dead now. Nobody does that anymore. Right? That's okay. Anyway, so I used it to denote number. Okay, number of configurations. This is the pound sign or something like that. Anyway, I don't care. Number of configurations on the x-axis. Configurations. Okay, here we go. What I want you to do is I want you to put the two states, the initial state and the final state, on this diagram. It's a diagram, not a graph. Now, first, let's consider the potential energy. Okay. Potential energy. Okay. So, where do we have a higher potential energy, in the final state or the initial state? Everybody, please. Just one last thing. Okay, where do we have a higher potential energy, in the final state or in the initial state? Thank you, the final state. All right. So what I would do is I would write like this. Okay. Final state has a higher potential energy than the initial state. And how do we know that? In the final state, we have gas. Gases have the highest number of configurations compared to any other phase. That's the idea there. By the way, when it comes to number of configurations, gases call the shots. All right. Now, number of configurations. Okay. Where do we have a higher number of configurations? Final state or the initial state? Everybody. Thank you. The final state has a higher number of configurations than the initial state. So I mark that there. Now, what I want you to do is I want to put this information in my diagram. Okay. The final state has a higher potential energy and higher number of configurations, meaning it should be higher vertically and also higher horizontally as well towards my right direction. Therefore, I would put that over here. Final state. Okay. And then the initial state should be diagonally across it over here. Okay. So this should be our diagram. One last thing, I promise. Now, what do we call this diagram? Okay, thank you so much. We call this potential energy versus number of, that's too much, right? So instead of calling this potential energy versus number of configurations diagram, I'm going to call this diagram from here on out PEC diagram, or in short, peg diagram. Okay, this is what we call this infamous peg diagram in 151. There you go. So we'll start from here on Thursday. Bye, everybody.